Renewable energy is clean, but overcoming the difficulty that comes with the fluctuation in its input has been a challenge. Current storage methods are surrounded by a plethora of issues, such as the reliance on scarce materials in lithium-ion batteries to the need for mountainous terrain and arduous civil engineering works for pumped hydro storage. But what if, instead of using mountains and lithium, we made our buildings like batteries? My proposal, SolarGrav, aims to utilize the power of both the sun and height to store electrical energy retrieved from the sun via solar panels as gravitational potential energy. Light absorbed in the panels generates a current through the photovoltaic effect. This current in turn is used to spin a motor that pulls a mass of 2 tons up an emptied lift shaft. This means the energy transferred from the sun can be stored as gravitational potential energy. A controller uses real-time data reflecting energy consumption in the building, and when demand is at its peak, the masses are dropped, spinning the motor shaft, now acting as a generator. This releases energy that can be used to power appliances throughout the building. Assuming the height of the building is 100 meters, a single 2-ton mass could store 1.96 megajoules of energy, which is equivalent to 0.545 kilowatt hours. Assuming the motor has an efficiency of approximately 95%, the electrical energy to lift one mass would be 0.574 kilowatt hours. Therefore, a system containing 20 masses would require roughly 11.5 kilowatt hours. Assuming a high-rise building has roughly 200 meters squared of rooftop solar panels operating at an average output of 5 kilowatts during periods of sunshine, it would take roughly 2 hours and 20 minutes to fully charge the system. Considering the fact that in winters, most cities in the UK receive 4 hours of daily sunlight on average, this means sunlight could charge the system fully almost twice in one day. During the descent of one mass, the generator output may spike due to variations in the descent velocity. To overcome this issue, we could use a supercapacitor to absorb sudden surges of electricity from the generator and release the energy at a controlled rate, maintaining a stable voltage and protecting the building's electrical system from power fluctuations. If the system recovers approximately 90% of the gravitational energy stored by the masses, then the system could deliver around 10.4 kilowatt hours to the building. This is sufficient to power essential building services or multiple household appliances. For example, it could operate 100 LED lights at 10 watts each for approximately 100 hours, a 150-watt refrigerator for around 70 hours, or supply a 3 kilowatt kettle for 3 hours of continuous operation. Although the system cannot replace large-scale grid storage, its purpose is to reduce peak electricity demand, provide emergency power, and allow skyscrapers to store renewable energy locally without relying on scarce battery materials.